Thank you. It is, of course, an honor to speak in this building, and I must say with a great sadness, because the work and everything, it is due to Vadim Alexandrovich Malyshev. Even my being here right now may be due to him. So he was, of course, my teacher and a friend for many years. The problem that I will speak about, it comes from Vadim Alexandrovich. I must say that I followed maybe all his topics, what he was working on. And sometimes it was not actually deliberately. Sometimes by some random walk, I bumped again into the same problems. But with this particular work, I am really sorry that I was not in time to speak about this result to Vadim Alexandrovich. So, okay, I will start with the talk. So it is again like all these three previous talks of this session, they devoted to Gibbs distribution, but it is now on the Coulomb gas. So if I stay a little bit there, I think it's okay. So what we will have, I will describe the system. Now it is system on a line. It is a Coulomb gas, but Coulomb gas with the interaction like three-dimensional Coulomb gas. First, I say these are the vertices on the line. I think I need my hands. So, and we consider the following potential. So there will be eventually Gibbs measure, but I will show first what is here. So these are the points on the line, but it is a segment of 0, 1. This is not a lattice anymore, it is interval. And the energy of the configuration in these points is given by the equation by this form. What is here? The betas, they are coefficients, constants, positive constants. V is potential or interaction potential between particles at point I and J. We will say that these are particles in the points y0 up to yn, and we say that two particles in the end are fixed. The rest particles, they are distributed randomly. That will be later. So this potential V, it depends on the distance between two particles, particle I and particle J, and that's an external force. And beta is J minus K. J minus K, that's the misprint, obviously, it should be I. Thank you. Thank you. We will move to another form. Thank you. So V is a pair potential.
Y capital and Y small are the same.
Y capital, I don't see Y capital anywhere. The second line. Y capital. Oh, okay, Y, not I. Okay, the capital, they are for random, and the small, they are for the configuration for the points in R. So this is a very general form, but let me move to another. It will be more precise, because of course there will not be very general V, but this V in the form of a real Coulomb repulsive interaction. It is 1 over distance. So the particles, they try to push each other. It is because beta is positive, and when S is 0, and it is infinity. So this no absolute value, because Y's are ordered, and I take the okay. It's another misprint. I will move to another one quick. Okay, do not. Okay, yeah, I should put then the range. K will be actually finite here. Typically, K is entire n, but here I will consider only finite n, and that's, we say, the range of interaction. And this force, external force, is a constant. It doesn't depend on S. It is constant. So let me rewrite it in a different form. So having that potential U, we will look for the Gibbs distribution with this density. So now we will have density of a random vector on the interval 0, 1, and that's in one more time I rewrite it. So here J is greater than I, so J minus I is positive, and this Yj is greater than Yi. So that's the potential that we are looking at now. This Coulomb gas form was actually introduced by MALYSHEV, and he studied actually the ground states for this density. He did not consider density. He was studying only the function U. What we are interested is also like these droplets, the configuration of particles, where they will be. The function is Gibbsian density, but how they will be spaced? Are they the particles? Do they cover the whole interval? And of course, we'll go to infinity. Or they will be in some clouds or some other configurations.
They are repelling.
Repelling. As long as they're repelling, they, of course, naturally want to stay equally spaced. But we have external force, and also we want to see the fluctuations of this repelling. So that's the major question here. To see the what is the model about, and to see some features of that. Here is a very useful representation. So I rewrite once again what I will do now to take out the part which depends only which doesn't have any interaction. So this depends only on X case, and the rest well, like sorry, what I want to say, that here we were looking for the density of vector Y, and the potential was depending on the distances between particles. Now I want to define some auxiliary distribution. I call it the random variable, I call X, and the density I write actually from this U, but what I do, the differences between Y's, I replace by X's. If I draw a picture, so we had there was a line 0 to 1, Y1, Y n minus 1. And now from the variables Y, I come to the variables X. And here is X1, X2, and that will be Xn. So the now it is okay. It would be nice actually to keep them. Then I can refer also to say, oh, very fine. Thank you. So we look now into this form. So in this form, what we see that that the first term that concerns only the axis. I mean, not the pair interaction. It's only the part which is factorizing in K. The rest, that's real interaction. So what happens now? If we look for the distribution of a vector of Y, it equals in distribution to vector x, but conditional that sum of x's is 1. Of course, it's better form in many cases, particularly if this x's would be independent. But now this form really highlights the meaning of a k. So observe that if k equals 1, so that if we take only nearest interactions, nearest neighbors interaction, then this whole term is 0, and the only part is left is here. And in this case, we have x's independent, and we would study y's through independent x's conditional on their sum. So that's, of course, much easier task. Now I want to write it in this form. So from this previous slide or previous representation, we can get that we can study density through the density of conditional. And now that's what I said. If k is 1 and f is 0, then each here this term doesn't depend on k except this xk, but the form is same. So then xk's are IID with this density. If k is 1 but f is positive, f is external force, then xk's are independent. They're not identically distributed, and that's their density. However, when k is greater than 1, then no matter what is f, even if f is 0, then the xk's are not independent anymore. So that's the interesting thing, that coming from nearest neighbors interaction to the next order of interaction, that's actually changes completely the picture. And even intuitively, physically, it seems like there is nothing really different. Apparently something is. So I want to say that how the history of these studies. For the nearest neighbors, it was only, previously it was only for the nearest neighbors. And this when temperature is, this inverse temperature, of course, when the temperature is infinity, then we study only, then this U, I should show where this T came into place here. If T is 0, that's inverse temperature would be, then the whole density measure, or the whole measure would be concentrated in the minima of U. So therefore, this U, they provide the minimum of U, provide the ground states. And that was discovered by MALYSHEV, that this model is very rich for phase transitions. He found 4 different phases. And then when temperature is positive, strictly positive, then MALYSHEV and Zamyatin, they studied case when there is no external force. When there is no external force, then of course phase transitions are along the force. So here that was not concerned. They studied the fluctuations and the order of fluctuations. And then for arbitrary f, it was I was working also on that. But now we will look also into something else. And I want to say that in general, of course, this this model is very very known. So these are just some papers related. So now let's look into before we come to the case of second order interactions of secondary neighbors. Let me say just very shortly. I will refer to what was written in this work, but it includes also previous works of Zamyatin and MALYSHEV. So indeed, as you say, that since they are repelling potentials, if we have small force, but you see, not very small, it could be up to O small of n. Then the particles, they tend to be to repel each other, as one could imagine. They cover interval regularly with order 1 over n. But maybe this is not so spectacular here, of course not, but most interesting here, the order of fluctuation, it is 1 over n cubed, not a square. And then what happens next? Then what we reveal this interesting feature. When we move to the critical force, and this critical force, it was actually this 4 beta n. It was also discovered in Malyshev's paper first. So when we take this critical force, what happens? If our external force comes up to this critical force, then the fluctuations are still same as it was previously, 1 over n to cube. But here we have already some constant, which is actually positive constant. And what happens that gradually one can see that increasing force, the particles are starting to move. They are moving to one side. So previous, you see here, it was 1 over n scaling, but above critical, the scaling becomes a little bit different. So here, I go to wrong way. Here, you see the 1k is of order constant, then the scaling is already of order 1 over root of n. So that's another scaling. Here it is possible to get, for me, only order of magnitude upper bound. And then if we go further, then it is another scaling. So when it is weak supercritical force, what I have here, then the differences have expectation of order constant, and these differences, I probably better draw on a picture in a second. So the first one is really of order constant, but the rest are still very small. I better, since I don't have a simulated picture, I will draw it here. So the first picture was for the small interaction. This is when f is of order much less than n. Then when f goes up to f is of order f critical, so there's some 4 beta n. Then what happens if the force, say some wind blows from one side, the particles are starting to move a little bit to one side, and then there are only 5 phases. Then this force, when it is just above critical, the first one is of order constant, and then it is almost equally spaced, starting from order of root of n. And when finally, when we pass some critical n particles, 1. They go up to, this is only first one, so they are not regularly spaced anymore. That's right. You see that there is there is a k there, and this k. So this only for the beginning, it is of this order, and then they are of order 1 over n. Yes. And then when we come beyond the critical force, then all the particles are jumped to one end. They are all there. And I thought that this is really interesting picture, because it shows 5 different phases and very clearly phase transition. Then the question is how it will be when we include the next interactions. And it was, for me, it was almost obvious that nothing interesting can happen in that case, but something else apparently comes. So that's what I want to say now. So if we take now the secondary interactions, as I hope I convinced you that this case is difficult enough to look at first, even without F, without external force, and not even taking further interactions. So let's take K equals 2. That's the second nearest interactions. So, and I will write this potential in this form so that if we neglect the rest, it is just as it was previously. So here is beta, and the secondary interaction I will write gamma just to see visually what comes from the secondary interaction. Physically, of course, the natural thing to say that gamma is beta, or at least not greater than beta. But also here, due to these boundary effects, let us take for the beginning also the circular version. So we add this term so that the particles now on the ring to avoid the boundary conditions. And we study also the density in the Gibbs form. Here, this round thing here, it is to mark that it is a circular distribution. Now what we have, of course, then at least we have this evenly spaced picture. We don't have any external force here. So if the particles on the ring, no matter how many next neighbors we take, one may believe that it is 1 over n, the expectation. Next, what comes for the structure of covariances? Here it comes something for me at least unexpected. So if we define this constant gamma in the form of a function of beta, constant delta, sorry, as a function of beta and gamma, those parameters that were featured before, that's the form, and then the covariance between the spacings between the particles. So what is this covariance? Let me also again move to my picture. So here I put them on the ring, and we take somewhere J, K spacing. Here would be Yj. Yj plus 1, yk plus 1, and we look for the correlation between these two intervals. By the way, in the previous case, when k was 1, the correlation did not make sense because well, it was 0 because we saw that the differences as x's, they were independent. So in case k equals 1, this correlation structure was very easy. It had the order much less than 1 over n cubed. We will see it later. So here what we will do, we'll look for this covariance, and what happens here, it is actually possible. So Mikhail yesterday said that it was interesting to see the model which is exactly solvable. So I would say also I was quite surprised that this yes, this one also simply formulated and exactly solvable. But if you saw that it was 5 years passed from the first paper on that topic. So okay, I will say it a little bit later how to prove it. So here, what is interesting that we can write in terms of this delta. We write this covariance. So what is here? Here it is this constant. Delta is less than 1. So this is all positive, positive. What do we have here? 1 over n cubed. It was as before, but what is there. That's also important. J minus K and this sub-index is just the distance on the circle. What is important that it is minus delta. So that means that the covariances, they have very peculiar structure. They are anticorrelated if they are next position, and if the distance between them is odd, then they are positively correlated. Well, if you think twice, it is convincing that it should be like that. And what is here? 1 over n cubed, the order of correlations. Say if we start with the distance very small, or even with the variance, so in the variance we recover almost formula as it was previously. So previously gamma was 0, so that's exactly the same formula as it was with the extra term. But now what is here? Also observe that if gamma is 0, and gamma is a parameter of the interaction with the terms of the secondary neighbors. So when we don't have next order neighbors, this gamma is 0 and this whole delta is 0, and this term is well, this part is 0, and we have only order 1 over n fourth. So that's 1 over n fourth. That's the order also for that previous model for the covariance. But what we have here, that the covariance for the first terms, it is still of order 1 over n cubed, just as a variance. And it has also a sign which is changing from minus, plus, minus, plus. And also what is interesting here, when this j minus k is increasing, the order of covariance is changing. So I made the subtraction of this here. So what we have out of that formula, that when j is k, the variance is of order n minus q. When the distance between the spacings is up to order log n, the covariance is of order n minus q, but here is a term which is exponentially decaying. So that means when k minus j becomes very large, then this term is not the major, and the major term is n to the power minus 4, and it stays with the minus. I think that we have some echo here. It's okay. Okay, sorry. So that's that was the consequence of that formula that we had previously. No, this doesn't work now. I think my pointer does not work. Oh, okay, now it's, sorry. So that's what I want to say, that I have 2 minutes or so. Thank you. So how to prove that formula? I was actually very surprised and very glad that the method was to find this Gaussian approximation. In fact, it is, if you remember, there was a book by Fedoruk. It is very much in style of that method of saddle point. It is really through the approximation. So what I wanted to say before that, I said already that in our case here, we do have conditional distribution, but it is like we are looking for the central limit theorem of dependent random variables. And when we have dependence, there are no, say, standard motives to prove it. So one of the first things that I humbly thought to do to get the exponential decay of correlations. And I really believe that after you get the exponential decay of correlations, everything in mathematical physics goes fine. But it was not even not on the way to prove any CLT or something. And the matter is here, I also never accounted this problem, but to get the lower bound for the variance, as you know, in the central limit theorem, we do need lower bound for the variance. And here it is still not so clear. So I cannot say anything about CLT for this case, but I can say that exponential decay for correlations, even for this system of x's, what I said, this if we take the vector of x, not conditioning that they sum up to 1, and we consider this vector of a dependent axis. So this this capital vector x is a random vector with the dependent components, because in this density there is a part which is not factorizing in K. But still, for this form of x, it is possible to prove or to derive exponential decay of correlations between the components. And of course, it is some ingredient for that theorem on covariances that I showed you. And that's for circular version. One can also from that derive same correlation. I think I'm about to finish all this, and I want to say that that was the first paper by MALYSHEV, which was very interesting on the phase transitions. And the theorem on the covariances that I showed, it is not yet published. It is uploaded in archive, and it will be submitted. Okay, if I don't have here, okay, this is that was for non-circular version, and this is for circular version. And here, what is what is here? Yes, it's one can get little bit different nuances for the circular, but principle is same, to get the exponential decay of correlations. So, but out of exponential decay of correlations, one can also, for the circular version, get convergence in. Okay, I better show. So this part here, n is the number of particles, and r here it's the number of if I call this xj, xk, say x1, well, but again, these bounds are nice, but to prove the or to derive the covariance structure, or to say something, for example, it is interesting to say something about central limit theorem, for example, for this axis. That's another story. Although we believe that this CLT works for them, that's now on the way. But I'm mostly interested about this covariance structure, and I would like also, if somebody knows this question, how to bound from below the variance. That's the most interesting. And this question comes on. Okay, I just told. Right, from it is actually here from here, because the covariance can be negative and it starts with the same order. So how to prove when we sum up? It seems like obvious when we sum up, it should be something positive, but I also can add that after that, I also looked even in one of the first papers by Vadim Alexandrovich on statistical physics. And in his work there, it was explicitly written, assume that the variance is positive. And it is now, I understand that this line is very, very much important. How to check this condition, I don't know. Thank you. I'll stop.
Please, more questions, maybe some questions from Zoom. Oh.
Maybe possible to generalize more general potential.
Yes.
Repeat.
Yes. The question was, is it possible to generalize it for the different potential? This, I believe, yes, because here all what is used, I can't move, but very much it is the like a expansion, like a Taylor expansion of the here. So that's the expansion of this function around minima, and then of course it will work. It will be even easier because this repulsive is quite tricky in the behavior, but in principle, yes. I think may also say, since you asked, so the method to how I came to that, it is actually through this Gaussian approximation as a saddle point, decomposition in the minima. But here we have, when we decompose, usually this matrix is factorizing, but here we have secondary terms. The matrix is not factorizing when we have secondary term conditions. And then I started to read some works. I thought it must be somewhere in statistical physics. And actually, in talk of Pavel Blecher, his co-authors, Itz and Devtz, and there was some other, they recently wrote a big paper on devoted to Brewery Kaufmann. And she apparently was working with on Zager, and she was inverting matrices. So here it was a lot on the Toeplitz matrices in the course of proof of this covariance structure. So I did have to invert certain Toeplitz matrix. And what is interesting, when you invert even 3 diagonal Toeplitz matrix, of course, the matrix of covariances is a fully covered. Therefore, we do have this covariance structure up to all of them. So all the terms are decaying. So that was the ingredient there. But I suppose that for other potentials, not Coulomb, the work might be even easy.